Can I get a quick show of hands? Like, who is more, just so I know, who is more on the architecture side of the house? Architects here, hands up. It's kind of hard to see. A fair amount. Who's on the development side? Okay, like actual coding, right? And any operators here, DevOps, SRE, whatever the title is, the smallest amount of people, right? So a little disappointment, I'm not going to talk about coding, right? I'm going to talk about like what happens, actually not really talking about microservices that much per se. I'm going to talk about like what happens when your microservice applications continue to evolve and get connected with other systems, right? Once you start composing things, right? You work in many teams, everybody deploys to production all the time. You get what we call a service landscape, and that's really driven by organic federated growth, right? Organic federated growth really means each team has the business objectives and you deploy new systems fairly organically. If you need something, you deploy it. 80% of whatever you need is already in the enterprise, right? You're just talking to it, right? There isn't so much a blueprint or a full-on architecture, but it has a really interesting couple characteristics that I'm going to get into. So now I want to really point out up front that organic federated growth is super important. It's a good thing, right? That's what gives you speed to build on top of existing things. But it also requires a totally different way of runtime control in operations, right? And to illustrate that, I want to start off with an illuminating story from old school operations. And it's one of these airlines things, right? July 2016, Southwest melted down. What happened is was one router out of 2,000 in a Dallas NOC just failed, right? And it failed in a weird way because it was, of course, it was monitored up the wazoo with agents and monitors, and all the lights were green, except zero packets out, billions of packets in, nothing coming out, right? So what happened is operations crammed, of course, and it took them 30 minutes to discover what's going on. 12 further hours of rebooting adjacent systems that had gone out of sync, couldn't catch up with what happened, had stale data, these kind of things. Meanwhile, all other systems that relied on those systems were down. Right now, flight crews couldn't get aboard because the data, how long they were in the air, were not available, right, and stuff like that. So really interesting, remarkable chain of events, and pretty spectacular outcome, right? One router, 5 days of downtime, $80 million of losses directly, like canceled flights and all that, hotels, and almost $3.5 billion wiped off the market cap, right? And there are two important learnings here, at least two, at least two. So number one is monitoring at the wrong level, visibility at the wrong level, right? All these green lights didn't mean anything, right? And the second learning is that you need to have control over system interactions, right? If they could have pushed back against these systems, if they could have, with the correct visibility, seen the incident earlier, seen all these packets coming in and nothing coming out, and then push back on the requesting systems until that was resolved, none of that would have happened, right? So both things important. Detecting really quickly, and then also having an ability to push back. And that's what I'm going to talk about, the criticality of mission control in complex service landscapes, complex architectures that are composite architectures, right? And there are three key terms. Service landscape, you're going to hear all over and over in this talk, right? And then characteristics of these service landscapes, which is really about stability and security that are different from normal applications. And I'm going to talk about this. Why is this a new reality that we're facing here? And then what can you do about it? Operational patterns, right? That's going to come up. I'm also going to talk about common strategies to cope with complexity in service architectures and why they don't really work for these composite architectures. And then bring examples about how you can remediate reactively with patterns and how you can proactively create new use cases and help yourself forward in the industry. Yeah? A little bit about myself. as Colin said, CEO, co-founder of Glassnostic. My previous company was a platform as a service and became Red Hat OpenShift, so I spent a couple of years at Red Hat, fully focused, of course, on like how do we build applications, how can we ideally support building applications, right? And there are two interesting things to me, interesting things that I learned, right? That from a technical perspective, all these applications that we've seen that were meaningful were not applications at all, right? They were all systems of applications. There's a tremendous amount of complexity going on. And the second was that the successful, again, from a technical perspective, successful systems of these applications were not successful because they were, well engineered. They were successful because they were operated well. Yeah? There was a great operations team behind it. They had the right levers, the right knobs. So that's what I'm going to talk about, and that's why our vision is really to bring runtime control to enterprises, to large service landscapes in enterprises. All right, so I want to zoom out. Why is this a new reality? How do these things come about, right, a service landscape? And I'm going to start with the new agile operating model that we all live in now, right? And this starts with like we are all working in small teams, self-managing autonomous teams. We have rapid decision and learning cycles, right? And then at the same time, we can really benefit from a vast cloud ecosystem with hundreds of Lego blocks that we can readily use. And then there's cloud native technology. We can put this all together, right? And of course, all these two pizza teams that we have now can deploy in parallel, right? So a lot of things, a lot of forward movement is happening in the space. And that has a profound effect on the architecture side of things, right? That has already evolved from microservices. Don't take pictures now, the slide is going to build later. Microservices, and then, to shared services, many microservice applications based on shared services. And then what are we talking about here? Organic federated growth, finally, service landscape. And there's this has also affected changes on like the control layer that governs how we connect those systems, how we connect these things. And that's evolved from old school enterprise integration to free-flowing APIs, extra middleware like gateways, and most recently, service mesh, right? And also, of course, on the operations side, where we have evolved from old school pushing of boxes to DevOps and then SRE, right? And then what we call mission control operations. So this is not just a set of individual evolutions. It is truly a new operating model where all these layers work together to support the agility of the enterprise. Okay? And that's what we're seeing more and more, that these architectures compound, they get composited, they grow organically, relentlessly, right? So I want to double click a little bit on now what is this service landscape. And here's an illustration. Right? It may start, it's really just any architecture that evolves through organic federated growth. And here's an example. If you take the first panel, right, it's a microservice application that becomes useful to other teams, so it gets other things bolted on. There may be a mobile gateway, another partner integration, other applications use services of that. So more and more applications are built on top of this application, right? And also new services, because now each service has a number of dependencies, right, or is a dependency to a number of the services. Now you start building out services, different versions of services next to each other, right? So that is really what organic federated growth is. And that has three really interesting characteristics. Number one, of course, on the security side, as we can all imagine, right? There's a total loss of perimeter, and the architecture changes all the time, right? So there's a loss of blueprint. I can't base my security policies on, what I know about the architecture necessarily, because it may not work tomorrow or next week, right? There's a fundamentally new challenge, right? And then, of course, these architectures have complex and very disruptive emergent behaviors, right? We know those as gray failures and so forth, but what they all have in common that they're large scale. There's a lot of systems involved and coming together, right? They're complex. Yeah? Just the number of systems is staggering. And each system behaves a little bit differently. So the chain of events, once you trace it, once you narrate it really, is very nonlinear, right? You get an effect that's blue on one side and on the other side it's green. And then that makes it very unpredictable. Right? Again, fundamentally new challenge, right? The question is how to stabilize it. And almost the most important characteristic is that you can't engineer your way out of it, right? We can't put parameters that are important for runtime configuration in a YAML file. Because tomorrow, some other team is deploying something else. No, this is wrong, right? So anything by the way of resource limits or like scaling behaviors, right? I want to have like 4 copies of that, right? Or scaling request behaviors, that many retries, and that's how how I'm going to back off. Or even like connection pool sizing becomes stale very quickly. And typically there's zero process around updating these things, right? Besides, you don't even know you're coding a service, right? And next week, some other business unit talks to you, right? So very difficult. We can't engineer ourselves out of this. We can't simply, in these rapidly evolving service landscapes, we can't simply define structure and set policies in configuration files and set and forget about them, right? So now, the key is really, I forgot about the clicker. The key is really that, ironically, the agility that the enterprises craves, right, ends up with an architecture that we can't control, right? And if we can't control this, of course, we can't operate it. And if we can't operate it, then innovation dies. So this operational crisis is the defining problem in the industry today. And it's the defining problem because service landscapes and their behaviors are the new reality that we're all facing. And the new reality is that in all these environments, failure happens overwhelmingly due to environmental factors, not to code effects and individual threats of execution. Right? So the code is subject to factors now that is entirely unrelated to it. Right? Those may be mentioned gray failures, any other kind of ripple effects, resource contention, right? All these things, very important that affect your code. And this is the new reality. And because of that, we need to step back and change operations. We need to be able to create structure and govern and detect and react at runtime so we can give the service landscape that we're supposed to run the systemic resilience that it needs, right? We need to be able to control disruptive behaviors, prevent systemic failures, and we need to be able to avert security breaches, right? So in other words, like an air traffic controller, yeah, we need to operate with a mission control mindset. Right? We need to care about the stability and security of the entire airspace, not about some ground operations. And in order to do that, we need to be able to detect and react in runtime, in almost near real time. And that means we need to base our detection and reaction on golden signals, on key signals, on metrics that apply to every single flight. Yeah. So we need mission control operations. This is what I mean when I say that all successful systems are actually run, not so much coded, they're operated. Right? Because the environment is what determines stability and security, and because the environmental factors are very unpredictable, we need to have this mission control operation system that allows us to remediate in real time. Again, I'm saying remediate, I'm not saying diagnose and fix. That's an entirely different process. This is all about real-time remediation, right? Fixing something. So what a triage nurse would do in an emergency room, right? Now let's now I want to look at some of the strategies that we typically bring to cope with complexity, right? And one of them is, of course, let's just continue as we did before. And that's typically like, you hear a developer say, well, I want to do this, like, Netflix does this way, and that's how we should do it too. Or, VP engineering comes in and says, well, I'm going to get my team not to write any bugs anymore, right? And clearly, upshot is like, Netflix is at the architectural, no offense, at the architectural level, a fairly simple application. Their problem is scale, right? Everybody here, for everybody else, the problem is the other way around. We have generations of complexity, and scale is probably not a top 5 concern, right? It's much more about stability and how can we combine all these systems. So it works to do nothing, to build distributed applications works nicely if we have single standalone applications. Right? Like a Twitter, again, simple application, conceptually simple application, right? Single blueprint. But it does not really work for decentralized service landscapes. The other strategy is, I got Datadog, right? I got excellent monitoring, right? And that's true. If you work at the lower levels of the stack, then a lot of these host metrics, node metrics, whatever is part of that package, is important. But again, it doesn't really work for a decentralized service landscape, which really operates on a much, much higher level, where I need to look at the interactions between services. So it doesn't help me to know what the heap size in a JVM is if really I have a large-scale gray failure going on. Right? The third one is, and that's a more newer one. How about, I trace into things. I get, it's a promise of like perfect visibility plus all the context that I need around it, right? And yes, it's true. As long as I own these services, tracing makes a lot of sense. But if I have like 20 other dependencies that I don't even know who've coded them, I don't really care about, it's just a service that I consume, tracing stops at that side, at that end. So tracing is a very local solution. Right? And then, of course, there's service mesh, right? And I love this image because, to me, it really shows how service mesh relates into a service landscape. So service mesh is really promising to deliver intelligent routing, metrics, policies, and encryption, security. And it is an odd solution because it is it gets you to the other side. So like this Baroque garden here, it gets you to the other side, but it's a very heavy solution. Right? It requires a very stable environment, and then it is very complex, it tends to be slow, and it's very invasive. So once you have it in place, unless somebody else manages it for you, it becomes very difficult to change. In particular, if you have many teams trying to inject YAML in the different envoys. Because a natural service landscape evolves much faster than that Baroque YAML. Right? So how should we operate these service landscapes? And this answer has 2 parts to it. Number one is because environmental factors are the determining factors today, and because they're so unpredictable, it hinges about real-time remediation. And that means we need to be able to quickly see and very quickly react. So the quickly seeing part needs to rely on metrics that are very easy to understand. Again, like the triage nurse. If you come in with a pulse of 160 and a temperature of 80, right? The nurse is going to put you down, into some other room, right? The nurse is going to give you some medication right there. So that is exactly what we need to do. And like in air traffic control, those metrics need to be universally applicable. They need to be very holistic, right? Air traffic control, it's very clear, need to be applied to any aircraft, right? So that's typically position, it's altitude, it's direction, it's speed, that kind of sort of thing, right? For cloud traffic, we need to apply it to any interaction. And that includes number of requests, how many requests are on the line, right? On the interaction. The latency of it, how long does it take, right, to be fulfilled? Concurrency, how many are in flight at any given time? Yeah? And of course, bandwidth. And by correlating these things and examining them, you can find anomalies. And those allow you to react very quickly, right? And the reaction part is relying on operational patterns. Operational patterns are really encapsulations of best practice remediations, right? And some of them here, examples, a bulkhead, right? I have several availability zones, and I want to make sure as an operator that whatever happens on this side shouldn't like slosh over here, but maybe at the same time, like, you know, critical service should be able to fail over, right? And we all know that happens all the time because misconfigurations happen. And then something talks from this zone or region to the other region, and nobody notices, you know, for another like month. So very important pattern to be able to do this, right? Another one is backpressure. If you have very spiky workloads or just too much demand at a given time, the ability to be able to push back against it for a certain amount of time relieves stress from these attacked systems, right? Whether it's malicious or not, it doesn't matter at this point, right? It's just a very quick remediation. Very important pattern. Segmentation, of course. We think of segmentation as a security tool, right? You know, these services can't talk to these services. And that's true. But it's also a pattern that's eminently useful to partition request clients, right? And so forth. Circuit breaker. Interesting pattern because we think of a circuit breaker typically as a developer pattern, right? I'm running an e-commerce site. There's a recommendation engine. If that's gone, I don't care that much. I can just circuit break around it, right? And that's true. But from an operational perspective, it's a slightly different use case where I may have a Hadoop cluster going on and I just realize it's going a little slower than it used to. So I'm now going to circuit break all the tier 3 services that are not that important and only the long-running queries of those. That's an operation concern. And so forth. There are a couple more of these. Another interesting one is, of course, the quarantine, because it's such a risk mitigator when it comes to deploying new code, and so forth. I'm not going to run through all of those. Let me turn to examples. So how does this actually look like in real life? And going back to the example from earlier, the story here that actually happened is a new deployment, a new piece of organic federated growth was added. And that affected the upstream dependency. In fact, what it did is the developers just swapped 2 calls, right? Because one took longer, so it would be sent off earlier. And that changed the fan-out pattern of this upstream server in such a way that the cache behind it, a shared centralized cache, started thrashing. Not immediately, but significantly higher, right? And that caused widespread, very unspecific slowness on the other side of the landscape. How does the remediation look like here? First, we need to be able to see very quickly that slowness. We need to see this. And then we need to identify the downstream bottlenecks. Where might it come from? Correlate with a deployment history, and then, of course, quarantine that deployment until the issue is then diagnosed and then fixed. Another really interesting example, love it, was published like about a year ago, happened at Target, a cascading failure at Target. Anybody here from Target? Good. So, really good. It's eminently important that these things get published. So what happened, and I'm simplifying, it's a long blog post, the URL is on the slide, 2 environments. One VM-based running an OpenStack and a massive amount of Kubernetes clusters. Historically, a couple of these clusters were really big. Typically, all the other ones were very small. So now, each workload on Kubernetes had a sidecar injected that did logging to Kafka systems. The Kafka systems running on OpenStack, obviously. So now the OpenStack guys came and said, oh, we need to do some neutron upgrade, right? It's going to be like 30 seconds or a minute or whatever downtime. Of course, that lasted more than a couple hours in various ways, very detailed apparently, and that caused the Kafka systems to be intermittently available. Now, of course, all these workloads on Kubernetes tried to continue to log, right? And they couldn't log, so they would wait till Kafka came back. When Kafka came back intermittently, everybody would log at the same time, right? Because, of course, the sidecars do the right thing, right? They log at the same time, and that didn't overwhelm the network. It caused a CPU spike on those nodes. And that CPU spike squeezed the Docker daemon. And now, of course, Kubernetes does the right thing and says, whoa, this node is unhealthy. I'm going to have to migrate this off to another node. And of course, the migration patterns are not uniform, so some nodes now had the same thing happen again. Now, these parts had to be moved somewhere else. So the outward behavior was, Kubernetes, why is my Kubernetes flip-flopping? Yeah. And the remediation should have been to very quickly identify logging spikes and then exert backpressure against those loggers, which really means just smooth it out. Don't let them all log at the same time, right? Delay individual things like over a second or so. And maybe even like if you have a long-running hanging request, circuit break some of those, right? Third example of remediation is like, and this is something we did for a high-security video conferencing environment. The architecture is roughly like it's on the left side. Many organizations on the same umbrella. Each organization, their own video conferencing rooms. And typically, participants would come in, going through a gateway, hit a bunch of relays for each media type, a different relay, and then it would be relayed out, right? And you see a node diagram on the right side, how it looked like. So typically, very important that participants would only talk to one video conferencing room at the same time. So now, looking at golden signals, you can see that there in the middle, there's like a bunch of clients, participants, with red lines that reach all over the place. And so clearly, two things going on here. One is there's a DOS happening, some sort of DOS. And the other thing is that there's segmentation violation. They shouldn't be able to talk across these things. Could be a misconfiguration, could be anything, could be a vulnerability exploit, whatever. Right? So remediation is identify the sources very quickly, based on golden signals, and then apply an operational pattern like segmentation to prohibit these clients from continuing. So those are all operations that you can do to stop the bleeding, right? But being able to operate and control in runtime is also very useful if you want to move forward and accelerate the development. And one of these ways how you can do that is by deploying to production. Right? The reason most people cannot deploy to production and need to stage services is because once it's deployed, there's nothing I can do. Right? I don't even know what's running. So we built these staging environments that are very difficult to build and actually make meaningful. So then there's systems around where, okay, I'm storing real user traffic and play it back in staging the other day, right? And I resort to tricks like that, but then it's too expensive, so my staging environment is only like a third of the size, right? So it's very quickly becomes meaningless. So, but because real-time runtime control is such a massive risk mitigator, we helped a online travel company to completely eliminate their staging environments. Another use case that's my favorite and really interesting is you can architect in real time. Right? And we did this for a connected car company, actually a car manufacturer, a connected car group of a car manufacturer. And what their problem was, I'm going to double click on that, is hundreds of applications on the left side here trying to call into millions of cars, or like data from the cars, depending on the functionality. Right? And this is an oversimplification of the situation. Right? This number of applications is growing about 200% a year. And it affects everything from managing the brakes to entertainment to autonomous driving, right? To all kinds of like monitoring systems on the car. There's like way more systems than most of you probably think. So their problem was, of course, we can't let these applications talk to the car, right? Security reasons, all kinds of reasons. So we need to intermediate it. But whatever we put in the middle, whatever we architect here, is going to be wrong next week, right? So now I'm putting a system in the middle that the next application comes in. It's super important to support this application. And now we need to touch all these services. Now we need to recertify all this stuff because it's talking to cars, right? So they took the plunge and decided we need to entirely avoid architecture. So, and that's kind of hard to do. If you look at this diagram, a lot of concerns that need to be taken care of. But they took the plunge, and all these boxes here represent about like 200 services. And again, growing over time. And said like every new requirement that comes in, we're just going to deploy a new service next to the other ones, right? So there's an API gateway in the middle that then routes this application to this new version of that service, right? And really interesting because it allowed the manufacturer to massively accelerate the deployments, right? Of course, end-user applications, right? Which would have not been possible if they had like designed this upfront. Very expensive design architecture upfront, and most of the time you don't know at that point what it needs to do afterwards in runtime. Right? So another case that's interesting, that was a cloud provider where the ability to define structure was important. Because all these architectures are growing, sprawling more and more. So it reach into different cloud services. Now there's serverless attached to it, right? So it's what used to be a VM is now Kubernetes, containers, and now serverless attached to it, and then all these applications come together. How they could define and segment their individual clients became very, very difficult. And they used to do this with just plain SDN, and of course at some point you configured SDN into a corner. So you reach multi-data center issues, different service issues, and so forth, right? So they used segmentation to do quite a bit in that area. Very important, again. So in summary, what I talked about is like how we now live in a completely new agile operating model. Okay? We work in small teams. It's like fast cycles. We have these immense amount of like cloud service at our fingertips. And everything happens in parallel. That is really the key driver, right? And that creates organic federated growth, the result of which is this new reality of a service landscape. And the new reality is that in service landscapes, everything depends on the environment. It's very easy to fix a code somewhere, right? But the individual thread of execution in whatever service you're looking at is not that important anymore, because all your failures really are determined by the health and how many gray failures you have and how many discontinuities you have in the environment, right? Then I talked about some solutions that we typically apply to complexity. Right? And that's, of course, like, we're just going to wing it. Then there's the monitoring, like invest heavily in monitoring. And that really only works in the lower levels of the stack. The winging it really only works for simple applications, right? Then tracing was another solution that is popular, but really only works at the local context. For the services that you personally own or responsible for the services that are in your repo, right? It doesn't work for any other dependencies. And then service mesh, which turns out to be very complex, very slow, and also leads to brittle architecture the way how it's invasive. And the real solution is to really aggressively invest into rapid MTDR, rapid remediation. Right? Being able to detect quickly if something happens before it becomes a real failure, looking at gray failures, and then being able to, and basing that on golden signals, and then applying operational patterns to quickly remediate it. Again, remediation is not a root cause fix. Remediation is remediating the situation, get it back to some form of normality. Right? And then I brought a couple examples, retroactively how to apply patterns, how can we remediate existing issues, and then proactively, what else can we do with runtime control and applying operational patterns. So takeaways for those of you who are developers and may not face this new reality yet is that absolutely everybody should avoid building distributed systems or solving distributed systems issues. They're very difficult to solve. Most of them are solved in some kind of infrastructure already and become very expensive. And most importantly, they kind of force a new waterfall thinking on you. Right? Those things need to be designed. There's a long ramp before you can deploy that. Right? It slows everything down. It's almost like serialization in a multiprocessor system. Instead, build resilient federations based on standard domain-driven design. Right? Federations of services, of course. And then anything that might happen, build compensation strategy. Heavily invest in compensation strategies in code. That's the best thing you can do. Something doesn't work quite right, make it so that the service degrades instead of failing. A typical issue that comes up here is if shops that have really great infrastructure related to using mocks, like stubbing out dependencies, typically have the worst compensation strategies in the code because it's so easy to mock them up, so everything is always there. If you actually need 5 nines of certainty that a certain result comes back, needs to be done with redundancy, yeah? And plausibility checks, checking several return values, kind of like airplanes do, right? Any important decision is done by 3 systems at the same time. Debugging and tracing ideally should be totally kept to the unit level. Right? It's very easy to debug code at the unit level. It's very cheap to do so. It becomes very hard, and it becomes very expensive later on in production. And most important of all is, by all means, defer design decisions to runtime. Right? Don't try to solve runtime concerns of code and services in your own code. Now for operators, the most important thing to remember is focus on the environment. Stop debugging individual nodes. Right? Focus on gray failures. What can you see? Yeah? How can you rapidly detect and react to things? Right? Investing in that capability has massive returns. And also decide which signals do you want to look at. What is the set of signals that maybe for your company is the most important one? I'm not talking KPIs that are customer-facing KPIs, but from a stability and security perspective. And what kind of patterns do you want to apply, and how fast, how quickly do you want to do it? And again, the quicker you can apply a pattern, a remediation, the easier it is to deploy something. The easier it is for your company to make forward movement. And then this is one of my favorite ones. Everybody talks about root causes. Stop. They don't exist. There's no root cause. If there's a root cause, it's a trivial bug. Like with families that are dysfunctional, there's not a single person at fault. Right? You unit test all your stuff. It all works. You put it together. It doesn't work. So forget about root causes. It's always a confluence of factors. It's intellectual laziness, frankly. I think it's just really lazy. And we as engineers, we're trained to jump on the first thing we see. Right? So typically it's a rabbit hole we love to jump into and then spend days chasing a bug that is not even that important. Instead, focus on remediation. Because in these systems, these systems are so complex that you can't chase everything anyways, right? Things happen. And most of the things, if you think your system runs clear, you're not seeing the gray failures. Right? You're not seeing the discontinuities that happen all the time. And last, no, almost last, don't do any process debugging. If there's a suspected bug in some code, some file handle is not being closed, it's not your job. It's the developer's job. All these together allow you to truly architect at runtime. Make expensive design decisions, resolve them at runtime when you have the data, when you see how it's behaving. And this, of course, applies to all decentralized architectures, not just microservices. So any combination of serverless, any combination of like VMs or mainframes or like metal systems in different data centers, in different regions. The fact that these systems all tend to come together now is really what the new reality is all about. So just to drive this home, Apollo 13 didn't make it back to Earth because it was well engineered. Right? It came back to Earth because it was run. It was mission controlled properly. Yeah? Operations is the key driver here. And the Southwest Airlines could have completely avoided this disaster, this meltdown, if they had the same type of mission control operations. If they had had a way to quickly see at the right level what was going on, not deep observability, high cardinality, high scalability, high dimensionality, whatever, high dimensionality, at the right level, granular level. Then they could have seen billions of packets in, 0 packets coming out. And then if they also had the ability to push back on traffic, to just slow everybody down until the system has been exchanged, right? This router in this case. None of that would have happened. Right? These 5 days of outage would not have happened. Yeah. Perfect. So, but they didn't have runtime control. Right? But you can, right? If you are an architect or developer who wants to like move some of those decisions to runtime, or if you are an operator who suffers from being completely ill-equipped to deal with runtime issues and want to get a semblance of control, talk to me anytime. I'm here. We're going to be at the open microservices space later on, I think in the last slot of the talk here. And of course, contact data, email me, or DM me. My DMs are open. Excellent. Thank you.